Okay, now welcome to the revision session on galvanic cells and electrolysis. So we'll just start off with a sort of a prelude to this, where we first looked at chapter 25, which talks about calorimetry. And it really relies on reactions converting chemical energy to heat energy, and we measure this heat energy in the form of a temperature change, so we can actually determine the energy released by the reactants, okay, or absorbed by the reactants. If absorbed, you get a reduction in temperature. You still get delta T though. In galvanics, chapter 26, we are really looking at chemical energy into electrical energy. Okay, and the whole point of galvanics is turning sort of an exothermic reaction, which normally releases heat energy, and separating the products of the redox reaction, the reactants of the redox reaction, so that electrons are forced through a wire, so we can get electrical energy. So if we just have a quick revisit of the dot point, using the electrochemical series to predict the products of a redox reaction and deduce overall equations from redox half equations. Okay, and also we've got to look at the limitations and maximum cell voltage. Now, if we turn our attention to the electrochemical series, I'm going to speak about it just for a little while. Okay, so I've got my one here. Now, we should know by now that oxidants are on the left-hand side of the electrochemical series, and reductants are on the right-hand side. In other words, these ones on the right-hand side can be oxidized. They can lose electrons. Okay, so for example, zinc, that can't gain any electrons to form a negative charge, but it can lose electrons. If you have a look, according to the periodic table, we've got ones that are likely to gain electrons with high electronegativity. So this is electroneg and electroneg. This is the trend that we see from year 11. Okay, so you've got things which are high electronegativity. They're likely to gain electrons, whereas these ones with a low electronegative are likely to lose electrons. So these are more likely to be oxidized, and they are strong reductants, whereas these are more likely to be reduced and are strong oxidants. So if we have a look at that here, we've got the ones in groups sort of 1 and 2 over here at the bottom, and they are the ones that are likely to be oxidized. So their reactions are more likely to occur like this, whereas the top ones are the ones that are likely to be reduced, and their reactions are likely to occur like this. Okay, so predicting spontaneous reactions. If we have a look, now, most of you guys know of the whole negative gradient, or Z. Okay, that's a good way to look at it. So let's have a look. For example, let's go iodine. Now, this is an oxidant, okay, quite a strong oxidant. If we pair it with lead, we see a spontaneous reaction, okay, where we've got iodine going this way and lead going this way. So it's kind of like doing a backwards, writing out a Z backwards, okay. So this one goes this way, this one goes this way, but it does make a Z shape. So if you have a look, we've got We've got iodine, solid, plus 2 electrons produces 2I negative. Notice that we've got these alternate arrows, but that only means that it can go either way depending on what it's reacting with. So for example, cobalt can be oxidized if it's paired with a strong oxidant, but cobalt 2 plus can be reduced if it's paired with a strong reductant. Okay, that's the only thing. So once you've picked your reaction, you need to put a complete arrow. So the two reactions will be this, and then lead will go in the other way. So PbS produces Pb2 plus 2 electrons. Okay, so if we write out the full reaction, the electrons cancel out, and it's I2S plus PbS produces 2I negative plus Pb2 plus. Okay, now let's talk about this type of reaction. The spontaneous reaction, it's likely to be exothermic, release heat. But we can harness this energy, this chemical energy, and turn it into electrical energy. Now I'll show you how. So iodine, we'll do another one for an example, two that are sort of more difficult. Let's pick a solution one. So Fe3 plus and Fe2 plus, all the oxidant and conjugate reductant are both in solution. So it'll be a solution half cell. Okay, and then let's pick F2, which we have something in solution. The oxidant is in a gaseous state and the conjugate reductant is in the aqueous state. For a galvanic cell, electrochemical cell, which relies on spontaneous redox reactions, we need to have the conjugate redox pair in each half cell. So in this case, we would have iron 2 plus and iron 3 plus in solution. In the other case, we would have F minus in solution. Then the gas is released through a special gas electrode, which has a piece of platinum, piece of something inert. Okay, inert means does not participate in redox reaction. Then you need to have an electrode on each side. So for the iron, you could use an electrode such as graphite, because graphite conducts. That's also inert. Or you could have platinum if you are rich. Okay. Then we connect the two electrodes. And we need to complete the circuit by connecting a salt bridge. Okay, so inserted into the gas electrode, into the input, we have F2. Okay, now let's see which way the electrons go. Now according to these two, this one's the strongest oxidant, so it will be reduced. In other words, the electrons will flow to the F2. So F2, we've got electrons flowing in this direction spontaneously. Okay. Now, they're going from the iron to the F2. So if we write out our half equations, this one will be written as normal. This one will be written backwards. So Fe2 plus produces Fe3 plus electron. This one is F2 gas plus 2 electrons produces 2F minus. Okay, then you have a look. Let's do the overall. Now for the overall, we need to make sure that the electrons gained in reduction equal the electrons lost in oxidation. So we need to times this one by 2. That's all I've done. So then you combine F2, so the electrons cancel out, F2 gas plus 2Fe2 produces 2Fe3 plus 2F negative, aqueous. Okay, but we've made electrical energy because we've separated the two half cells. Now we've got to start doing the nomenclature. So this one would be called the anode, as oxidation is occurring, and it carries a negative charge because electrons are flowing away from it. This is called the cathode, which carries a positive charge and electrons are flowing towards it. So reduction. Okay. Then we talk about where the ions are traveling. Now on this side, if you look at the half reaction, it's becoming more negative and electrons are flowing to it, so it makes sense. So to balance that charge, we need cations in the salt bridge to travel to cathode. Then we have anions in the salt bridge which travel to anode. Okay, then you can do something like determining your maximum cell voltage for this cell. Now, under particular conditions such as SLC and also 1 molar solutions, okay, under these conditions, so 25 degrees Celsius, etc., you do get a cell voltage, well, you should get a cell voltage of highest, so to work out voltage, highest E minus lowest E. 2.87 minus 0.77 2.1 volts. That's the maximum cell voltage. Okay, now let's talk about why positive gradients are not spontaneous. Okay, so if we look at a positive gradient such as zinc 2 plus and copper, sort of the opposite of Daniel cell, even if it were to occur, that copper would be oxidized into a stronger oxidant. That zinc would be reduced into a strong reductant, and they would undergo a spontaneous reaction. So the way we answer this is it's non-spontaneous as copper solid is a weaker reductant than the conjugate reductant of zinc 2 plus, which is zinc solid. So you're basically comparing these two, or you could say zinc 2 plus is a weaker oxidant than copper 2 plus. Okay, so let's start putting this into practice. So you can follow on with these questions. Now, if we read this question, in a problem-solving activity, they've got these particular reactions, but the E0 values are all messed around. Now, if you have a look, the objective is to correctly identify the E0 with these three. Okay, so what they've done is they've connected it all to a hydrogen standard half cell. Okay, and what they've done is compared them all to this, which is 0, E0 of 0. That means that if electrons travel to the test cell, that the test cell must have a stronger oxidant. Because as you can see, the stronger oxidants have the higher E0 values. Okay, now we analyze the results. Okay, for this one, the electron flow was detected passing from the hydrogen all the way to the test cell. Okay, which basically means that this is a stronger oxidant, as it would be more likely to be reduced than H2. And if you look at it, you can identify that the only one with the positive charge, that is greater than 0, is this E0 value. So that must belong to 0.22 volts to this one. Now let's check the other ones. The mass of the cadmium, first of all, before we check it, you have to know that they are actually below the 0 because the other two values left are negative. So these other two I'm predicting will go this way. Oxidation will occur at both of them as they are stronger reductants. So the mass of the cadmium electrode decreased. That makes sense, underwent oxidation. And the pH increased. Now let's have a look. This has nothing about pH because it has no H+. But if you have a look here, this one would be undergoing that way. So because it would be higher, stronger oxidant, more likely to be reduced. So therefore, we decrease H+ in the hydrogen half cell. Therefore, increase pH. So let's have a look at the answers. Questions. Explain why the other two values cannot be assigned to the half equations. So for this type of answer, you need to really talk about, You really need to talk about the fact that the other two are actually stronger reductants, but because they're both negative, we would need to have a voltage to determine the difference. What I would answer under B is, so both of the other half equations, E0 are neg, but need voltage to determine where they sit. So to determine the gap between them, you'd actually need to determine the voltage. Okay. Next one, explain why pH of the solution. Okay, so that's that answer there. Because we have H2, which is reduced, we decrease the H+ and increase the pH. Now this one, let's just try not to look at that yet. Okay, so here we've got 4 half cells. Okay, now we've got a positive electrode and a negative electrode, so they've told us that. They've also told us the gap between them, so I can tell copper and R have the largest gap between them. So basically it wants you to put them in order of increasing strength as reductance. That means from weakest to strongest reductance. Now if you have a look, the positive electrode will be where reduction is occurring, and the negative electrode is where oxidation is occurring. Okay, so oxidation will occur at the strongest reductant, because if you're a reductant, you're oxidized. So if you want to compare them, copper is a stronger reductant than P, so copper would be further down than P. Q versus copper, Q is further down, and R versus copper, R is further down, but we don't know where yet. So Q versus R tells us this because R is even further down. So the strongest reductant has to be R, then it has to be Q, then it has to be Cu, then it has to be P, which gives us option D. Okay, now this question. Okay, use the information in the electrochemical series to write a balanced overall equation that shows hydrogen peroxide acting as a reductant. So if we have a look at that, hydrogen peroxide acting as a reductant has to be on this side. It wants you to write a full equation, so you could do really anything. I'm just going to choose it with the same number of electrons so that I don't have to times it by 2. So I'm going to be picking this one as going this way and this one as going this way. Okay, so just simply write it out, electrons cancelling out. Okay, so after we've done that, let's answer the next question. Hang on. I wrote the H2O2 in the same direction. Nicely done. Sorry about that. Just to confuse you, they need to be swapped. I forgot to write it in the opposite direction. So let's write that out again. Very good. Now, next question. Using the data from the electrochemical series, a student suggests that a reaction will occur between copper and hydrogen gas. See, copper 2 plus. And hydrogen gas is the person right in their prediction. Where is hydrogen gas? Yeah. Yeah, negative gradient. To test this prediction, hydrogen was bubbled into an aqueous solution. No reaction was observed after 5 minutes. Please provide one possible chemical reason. Okay, now simply I would say the electrochemical series says nothing about rate of reaction. Okay, it gives no indication of reaction rate. Now they said in their answers, if I bring that up, they are saying You see that? So a lot of answers suggested non-standard conditions or not SLC. The only problem with answering that, we know that that's a limitation, but the answers do not show understanding because we need to actually talk about reaction rate. So you could be saying a concentration less than 1 molar. You could say a pressure of less than 101.3 kPa or a temperature less. Everything that would decrease reaction rate. So you can't just say not because you're not saying in which way. Okay, we have a look at the other one. Which of the following would be predicted to show to spontaneously reduce iron but not cobalt? Now, if we have a look at the electrochemical series again, let's find these two reactions. Now here, we've got lead ions. There's Pb2+, here we go. And we've got cobalts. Okay, which of the following would be predicted to spontaneously reduce? So we need a strong reductant for that. So tin or nickel, but not cobalt. So that would be a positive gradient. So either tin or nickel, and have a look. We've got tin here. And it's not tin ions because that's an oxidant. You'd need a reductant to reduce something. Okay. Now the next question. Which of the following is a feature of the standard hydrogen half cell? Okay. So basically the way the standard She cell is set up is we've got a gas, special gas electrode with a platinum PT, and then we've got 25 degrees Celsius because we've got SLC, so it's 298 Kelvin, and we've got a solution of 1 molar HCl to provide our H+, and then we've got I think that's pretty much it. No, pressure. So H2 we put in at 1 atmosphere or 101.3 kPa. Now let's have a look. So we don't use nitric acid as the electrolyte, we use hydrochloric acid. We don't use a temperature of 273, we use a temperature of 298. And we don't use a graphite electrode, we use a platinum electrode. And D, this is definitely correct. We definitely have to have hydrogen gas at 1 atmosphere. Okay, this question. So, copper pieces added to a dilute solution of hydrochloric acid. What would you expect to observe? Okay, let's have a look. Copper pieces are here. I almost want to change highlighters because I feel like it's getting confusing now. Just bear with me. I only have yellow. Just use this instead. Okay. So copper says, what would you expect to observe? Copper in hydrochloric acid. So hydrochloric acid is H+. Well, that would be not a spontaneous reaction. So what would you observe? I would say no reaction expect. So it's already said, what do you predict? Write a balance equation for any reaction occurring or explain why no reaction would be observed. Well, you say copper is a weaker reductant than the conjugate reductant of H+, which is H2 gas. Okay, and last one for galvanics. Consider the series of reduction potentials for the 3 half cells. So basically they haven't written it in order for you, that's great. This one would have to be at the top, this one would be next, this one was supposed to be down here. Which species is the strongest reductant? Well, the strongest reductant have the lowest E0 values, and the reductants are on the right side of the equation. Okay, reductant. So it would be Mn solid. Okay. And, oops, so write an equation for the reaction occurring in the combination that would produce the largest voltage. So largest voltage is strongest ox with strongest reductant. So if you have a look, strongest oxidants Au3+, strongest reductants Mn, but the only thing is the electrons are not balanced, so you'd have to times this by 2, times this by 3. 3, 6, 3, 2, 6, 2. Okay, then you simply write it out when you are cancelling the electrons, and you'd have to go this way for the reduction reaction, then you'd go this way for the oxidation reaction. So 2 Mn solid plus 3 Mn solid plus 2 Au3 plus produces 3 Mn2 plus 2 Au solid. Okay, let's just determine what that E0 value would be. Okay, so the highest E value is 1.50. So the voltage equals highest minus lowest, which is negative 1.18. So 1.50 minus negative 1.18 is 2.68 volts. That would be your E0 value. Okay, now I'm pretty sure that's all I was going to talk to you about galvanic cells. Okay, now we are getting into electrolytic. Okay, I'm going to do a couple of questions in class, but we'll do a little bit now. Now, if you read the dot points, it says the chemical principles, half equations, and overall equations for simple electrolytic cells, comparing electrolytic cells in molten and aqueous electrolytes. Remember that water can act as an oxidant and a reductant, just like it can act as an acid and a base, amphiprotic, and inert and non-inert electrodes. So, and then we'll do Faraday's laws. So, I had this up in class. The important thing I wanted you to know was that with electrolysis, we'll give you a little bit of a rundown. Electrolysis. So, it is not galvanic, it's not electrochemical, it is looking at non-spontaneous reactions. Endothermic, we know this because we require the input of energy in the form of electrical energy, and we convert that into chemical energy. We make chemicals. Now, why might we want to do this? 3 reasons. We want to electroplate. We want to electroplate. We want to extract metals from their ores. And we want to recharge batteries. Not only extracting metals from the ores, but also from molten environments. Okay, so let's have a look. Now, in electrolysis, okay, we are usually working with positive gradients, but we force electrons to the cathode. We are, in other words, forcing reduction. Okay, let's go into answering questions. Okay, this type of question might look a little bit difficult when you first look at it because it's got all sorts of things happening. But it's actually quite easy because you have a look and it's asking for the reductant. That is the species that is oxidized. So you can just use oxidation numbers for that. -2, -6, +6, +3 for aluminium, 0 for carbon, 0 for aluminium here, -2, so +4 to carbon, and carbon is oxidized. Where is it oxidized? Oxidation always occurs at the anode. Notice that the anode is positive. That is simply because when we put an electrolytic cell together, we get a power supply. Positive might be here. This is the carbon anode. The positive side of the power supply attracts electrons, so removes it from the anode, so oxidation can occur. And the negative side spits electrons out into the cathode, where reduction can occur. And in this case, aluminium oxide will be reduced, okay, from +3 to 0, and that occurs at the cathode, which is negative. Okay, let's have a look. So molten aluminium, alumina in molten cryolite. So all of this stuff is just saying we've put the, we get molten aluminium at the end, so we get some of it out. Now the important thing is with this electrolytic cell, it's all in one. Now the main reason for that is because we're not interested in getting electrical energy. So what's the point of separating the two cells? Okay, now the problem is a lot of the times we use molten electrolytes, and I'll tell you why. Let's say that let's have a look at magnesium. We want to get pure magnesium. So we want this reaction to occur. Locate it on your electrochemical series. We then want to get, let's say, we want to get chloride. And we want to use chloride to get chlorine gas. These are the desired reactions. And plus 2 electrons. Okay. Now, if I've got another electrochemical series, that would be great. No, of course not. Just because it is getting fairly messy. So, I've got one here which is a little bit neater. Okay, so let's have a look at where chlorine exists here, and we have magnesium. Great, non-spontaneous reaction, but no worries. We will force electrons onto the magnesium to force it to undergo reduction. So we might want to have something like this, magnesium, Mg, even if you've got inert carbon, even cheaper, carbon electrode. Then on the other side, you need to put in chloride. So basically inside we just have magnesium chloride in the aqueous state. And then what we do is we've got carbon on each side, and we connect it to an external power supply, and we want to go positive here, negative here, so the electrons go that way, and we want to have this reaction occurring here. We want this to be loss of electrons, so we want that reaction to occur there. The only problem with that, if you have a look at this, is that water is also going to be present, and it's going to be competing. Now, water is a stronger oxidant than magnesium. So in fact, you get the reduction of water at the cathode. So this is the cathode, and the half reaction will be 2H2O plus 2 electrons produces H2 gas plus 2OH negative. Now at the cathode, so the cathode is negative because it's connected to the negative terminus of the power supply, and it's still where reduction is occurring by definition. Then if you look at the anode is positive because it's connected to the positive terminus of the power supply, and it is oxidation because by definition oxidation occurs at the anode. But if you have a look at this, you actually have water which is competing as well, which is a stronger reductant. Because water is a stronger oxidant than Mg2+, it is preferentially reduced at the cathode. Then you have a look at the other one. Water is going to be reacting to produce oxygen gas, hydrogen. Hang on, I'm filming something. Why?
Are you torrenting or seeding?
Yeah, I'm uploading something to YouTube. Sorry. Okay, so 2H2O goes into oxygen. So I really want you to know these reactions. Like when you're in your chem exam, highlight these reactions. These are the really important ones. Water acting as a reductant here and as an oxidant here. Now it's a fairly weak one on either side. I mean, there's not many. These are the only reductants that wouldn't beat water. So but they might spring it up on you. Okay, now a good way to figure this out is like so. I just don't want to show you. Okay, electrolysis of sodium iodide using unreactive electrodes. Solution though. So we do have water. Okay, so what I would do when determining what it is actually write out your oxidants and your reductants. Now, list what you have. Sodium, iodide, water. That's all we've got. We don't have iodine. We don't have sodium solid, okay, because it's not written there. Now, you do your oxidants. We've got Na+, and we've got water. Water's further up, so I always write it further up. And as our reductants, we've got iodide, yeah, and water, which is further up. Now, in selecting which reaction is going to occur, you pick the strongest reductant. In other words, further down or highest E naught. And the strongest oxidant, which is further up, which is the lowest E naught. Oops, strongest reductant has the lowest E naught. Strongest oxidant has the highest E naught. My bad. Okay, so we pick the one that's furthest down and we pick the one that's further up. Now, in writing it out, so oxidant is reduction. It'll be undergo reduction. So the reduction reaction will be the water one, this one. So just simply copy that out. 2H2O plus 2 electrons produces H2 plus 2OH minus. Okay, then you go oxidation. Then that will be the I. So you simply grab this one, where is it? This one, and you write it that way. 2I negative. Notice that this is actually a positive gradient, but we are allowing it to occur because we provide it with electrical energy. Okay? So, keeping that in mind, let's start answering some questions. So for reaction, you're simply adding the two together. Let's start answering some questions. So, which of the following occurs during electrolysis of molten sodium chloride using graphite electrodes? Well, let's have a look. Molten sodium chloride is Na+, and chloride is Cl-, liquid because it's molten. Graphite electrodes inert, there's only one of each. So the two reactions will be, you'll get the reduction of sodium, molten, and you'll get the oxidation of chlorine to reduce chlorine gas. This is one that we actually went through in class. Now, the important thing is, molten is great, but the problems with molten, more wear and tear on electrodes. Okay, cations move towards the positive electrode. Cations move towards the cathode, which in this case is negative. Electrons move through the electrolyte. That's completely false. A gas is produced at the negative electrodes. False. Both cations and anions move through the electrolyte. Yeah, well, that's a giveaway. Okay. Which of the following occurs during electrolysis of a dilute copper sulfate solution using graphite electrodes? Well, let's write out the oxidants and reductants. Now, what have we got? Copper, it's solution. So we've got water, copper 2+, H2O. Is that it? Yay. Okay. So we've got copper 2+ should be a stronger oxidant than water. Yep. So I'd write that further up. Water. On the other side, you've only got water. Okay. So the oxidation reaction will be the oxidation of water. This one, going that way. So you just copy that out. Then the reduction will be this one going this way. So you just copy that out. There you go. All right. So there's a reduction at the cathode, oxidation at the anode. Okay, and the oxidation, because it's a positive gradient, it's electrolysis. Oxidation is positive, so reduction is negative at the cathode. So the cathode's negative. Okay, so the cathode decreases in mass. No, the cathode would increase in mass. Colorless gas is produced at the cathode. No, copper solids produced at the cathode. A colorless gas is produced at the positive electrode. Yes, oxygen gas is produced at the positive electrode. Always read on, make sure the electrolyte solution becomes darker. So what's making it blue or colored is the copper 2+. Because we're eating some of it, it becomes lighter. Okay. Now this question I actually really want to do in class. Okay, so we've only got a few left. Limitations of the predictions. So it's only valid under SLC. So you really have to remember these conditions. Concentration, 1 molar. 25 degrees Celsius, 1 atmosphere pressure, or 101.3 kPa. PV/RT. Okay. So that should be pretty much it. So also you've got to be very specific. Like if it says it decreases reaction rate, it's because the concentration will be lower, temperature lower, pressure lower. So you have to be really specific. You can't just say it's outside of this condition. Okay, so we went through this. So the concentrations also play a part. The higher the concentration, the more likely to react. I will go through that in class a little bit more. But for example, in the production of brine, in the production of chlorine from brine, they actually have chloride and water. Okay, they had this in a past exam question. It was aqueous, but they said it was very concentrated. And actually we got the oxidation of chlorine. So because it was higher than 1 molar, and it was quite a bit higher, we actually got the preferential oxidation of it. In the concentration is increased. Okay. Okay, now Faraday's laws. I'm going to be spending a little bit of time on Faraday's laws and then we're done. I want to start off just looking at this. So, we know that electrons carry a negative charge. Now, if we have a look at our data book, charge on 1 electron was found experimentally to be negative, see, because it's got a negative charge, 1.6 times 10 to the negative 19 coulombs. 1 electron carries a charge we're not usually dealing with 1 electron. We're usually dealing with moles of electrons. Let's put this in perspective. Let's say we're interested in electroplating. Let's set up a simple electroplating cell, the same one you did in class. Let's say we have copper. Oh no, let's say we have a spoon. That doesn't look like a spoon. Let's throw another spoon. So let's say that we have a spoon it has to be a metal spoon. It's very important for it to be metal because electrons will only flow through that metal substance or graphite. So it needs to be conductive. What we do is we want to plate it with copper. So we have a piece of copper solid. We then put it in a solution of copper 2+. We then connect it to a power supply, and we connect the negative side to the spoon, and we connect the positive side to the copper. Now what happens is, as you are adding electrons from here that have been removed from here, you're making this side more negative. What happens is the copper in solution is attracted to that side, keeping in mind that this works because copper is a stronger oxidant, and if we had a solution of magnesium, that water would actually be reduced. So copper goes that way, and we do get this reaction. And the other side, we are losing electrons from the strongest reductant. Again, copper is a stronger reductant than water. So this is reduction. This is oxidation. Okay. Now, you might be asked, what happens to the concentration of copper over time, or the color of the solution? Remains constant, as it's produced at the anode at the same rate as it's consumed at the cathode. This is important for us. We want to know how many electrons are going through, because we want to be able to determine what mass of copper we're depositing. Okay? That's really important. Now, so that's the charge on one electron. Now, the charge on a mole of electrons is called Faraday's constant, and it's accepted as, so that's a symbol, it's accepted as 96500 coulombs per mole of electrons. They're the ones carrying around the charge. This is really good because charge can be experimentally determined. From amps and time. So if you have a look, Q equals IT. This is coulombs per second. This is seconds. Coulombs equals coulombs per second times second. Seconds cancel out. Charge equals charge. This is great because if our charge is 96500, we know that 1 mole of electrons has gone through, because that's the charge that 1 mole carries with it. Now, your other equation, you know that if 1 mole carries this charge, 2 moles would carry twice the charge. All we're doing is timesing the moles of electrons by Faraday's. Now, these two equations are essential for determining these electrolytic calculations. Now, let's have a look. A classroom experiment was set up to simulate the extraction of zinc metal from zinc ions by electrolysis. In this experiment, 150 mils of zinc sulfate was electrolyzed Oxidation. So we need to know the oxidation. Now let's just make sure that we won't have water as a competitor. Okay, so we've got to do oxidants, reductants. Now what do we have? We have zinc, we have water. Okay, that's it. So as oxidants, we have zinc, but we also have water. Now I'm just going to see where water is compared to zinc. Oh, zinc is further up. So zinc will be preferentially reduced at the cathode. At the anode, we will have a reductant, water. Okay, now that will be that equation. So it's only over these two equations. So 2H2O produces O2 gas plus 4H plus 4 electrons. This will be the half equation that occurs at the anode, which is oxidation. Okay, now 39% of the state got that right. Okay, so just keep in mind you have to identify both water acting as both an oxidant and a reductant to make your decision. Now, let's have a look. A mass of zinc was produced. We realized that zinc is the strongest oxidant, so it'll be zinc plus 2 electrons produces zinc solid. Okay. Now, a mass of 0.9 grams of zinc is produced in 30 minutes. That's great because that gives us a unit of time. So it's time, and this gives us mass of zinc. This is pretty much all the information we need to know. It wants you to determine amps, so it wants you to determine I. Okay, now I've got the calculations already done, so just bear with me. Okay. First of all, you need to determine the moles of zinc. Mass over molar mass. 0.9 over 65.4, 0.01376 mole. Once we've determined the moles of zinc, we've determined this, we need to determine the moles of electrons. 2 over 1, unknown over known, times the moles of zinc. Think about it. The number of moles of electrons you have is going to have to be more, or equal to, if it's got a +1 charge, equals 2 times 0.01376, which is 0.0275. Now we have Q equals moles of electrons times Faraday's constant, which equals 0.0275 times 96500, which equals 2655.96 coulombs. Then Q equals IT. We want to determine the amps. Our T has to be in seconds, which is 30 times 60, so 1,800 seconds. And we simply rearrange. We want to know I, Q over T. QT. Okay. .48 amps. And that was the correct answer. Okay, so I think that this is getting to the last question, so just bear with me. Now, a teacher demonstrated, I love this question. Okay, a teacher demonstrated an apparatus. Okay, let's get it. So a current of 1.5 amperes, which is A, which is I, and for 30 minutes, oh, is that the same time? That's excellent. So 1,800 seconds again. T equals 1800. I can already determine Q. Anyway, let's have a look. XBR, molten salt. Molten salt only has X2+. I can tell that because it's Br minus. Br minus goes into Br. Oops. Yep. Goes into Br liquid. Is that the equation? Just got to make sure that you copy it straight out of your data book so you don't make any mistakes. So Br minus goes into Br liquid, very good, plus 2 electrons, and we've got 2 there. Then we have this, plus 2 electrons produces X solid, or actually liquid because it is molten. Okay, write a balanced half equation for the anode. That would be oxidation, so that would be 2Br. Liquid produces Br2 plus 2 electrons. Okay, now we need to determine the amount in mole of metal X that was deposited. Okay, so to determine the number of moles, you can start off with Q equals IT, 1.5 times 1800 equals 2700 coulombs. Then Q equals NEF. Rearranged, the moles of electrons equals Q divided by F. .028 mole. The moles of X, as you'll see, unknown is 1, known is 2, equals a half of the moles of electrons equals 1/2 times 0.028, 0.014. Okay, now to determine the mass, the moles. Actually, that's it. Identify metal X. Okay, so we need to determine the molar mass, and we can do direct identification. N equals mass over molar mass. Molar mass equals mass over moles equals 2.9 over 0.014, keeping your calculator, 207.3 grams per mole. Great, so it's lead. And 64% of the state got that question correct. Question 3. Let's just finish this one. So, calculate the amount in mole of chromium deposited. So what are we given in the question? Mass of chromium is this. 315 amps for 7 minutes. If you look at the chromium reaction, does it even have chromium on there? No? Oh, it's asking you to calculate the charge. Sorry about that. So calculate the amount in mole of chromium deposit. So moles of chromium equals mass over molar mass equals 0.264 grams over 52, 0.005 mole. Calculate the amount in mole of electrons. Moles of electrons equals Q over F. What's Q? Q equals IT equals 3.5 times 420, 1470 coulombs equals 1470 divided by 96500 equals the moles of electrons equals 0.015. Now, if you do that, like if you just have a look at it, we can do Okay, what you can do to find out the charge is you know that the moles of electrons will always be more, but you want to know basically chromium X plus X electrons produces chromium solid. You want to know these values. Now the way you can do it is just find out how many moles of electrons to chromium. So 0.015 divided by 0.005 is 3. That means we've got 3 moles of electrons to every chromium, so it must have, we're determining this ratio, 3 to 1, so it must have a 3+ charge. Okay, and last question, explain why it is not possible to deposit magnesium by a solution, and we answered that before. Magnesium is a weaker, or water is a stronger oxidant than Mg2+ and is preferentially reduced. And that's everything. I hope you enjoyed it.